All right, so for this problem, we're asked to calculate the surf similarity parameter, determine breaker type, and calculate wave run-up on a beach with a slope of 10 degrees with waves coming in that have a deep water wave height of 5 feet and a period of 6.5 seconds, right? So the first two steps are going to be to calculate the deep water wavelength, use that to get the surf similarity parameter, and then we can get the breaker type from that. So deep water wavelength is equal to acceleration due to gravity times period squared over 2 pi. So that's going to be 32.2 feet per second squared times 6.5 seconds all over 2 pi. And if we calculate out, that's going to come out to 216.5 feet. So once we have that, we can calculate the surf similarity parameter, which is going to be the tangent of the beach slope times the deep water wave height over the deep water wavelength, all to the negative 1/2 power. So that's going to be tangent of 10 degrees times 5 feet over 216.5 feet, all to the negative 1/2 power, gives us a surf similarity parameter of 1.16. All right, so 1.16 is greater than 0.5 and less than 3.3. Therefore, we have a plunging breaker. So now that we have our surf similarity parameter, we can calculate our wave run-up. So the equation that it gives you in the slides is that wave run-up is equal to the deep water wavelength times the tangent of the beach slope times the deep water wave height over deep water wavelength to the negative 1/2 power. However, hopefully you can all realize that this tangent beta h naught over L naught to the negative 1/2, well, that's just equal to the surf similarity parameter. So anytime you do these problems, if you've already calculated the surf similarity parameter, you can just do deep water wave height times the surf similarity parameter to get the beach run up. And that makes it a lot simpler and saves you from having to chug through a bunch of numbers again, right? So we can go ahead and plug in our deep water wave height is 5 feet times our surf similarity parameter of 1.16 gives us a wave run-up of 5.80 feet. Right? Now, the last thing I want to point out is what that 5.80 feet means, right? So let's imagine we have our beach, right? And if we look at the slope of our beach, we're told that the slope of our beach is 10 degrees. Or to be more generic about it, the slope of our beach is some variable beta, right? And we know that we have a water line at our beach, right? This is the kind of water level based on whatever our tides and whatever is, and our waves are coming in on top of that kind of baseline water level. So once those waves hit the sand, it's going to roll up the beach, right? You've seen this in real life whenever you go up to the beach. And what's going to happen is the water is going to rush up the sand, and then eventually it's going to reach its highest point where it doesn't have enough energy to keep going up, and then the water will rush back down the beach, going back to that nominal water level, right? So that variable r that we just calculated for beach run-up, right? That is the vertical distance that these waves can climb as they go up the beach. It's not the horizontal distance that the waves go, or even this tangential distance that they actually travel along the sand. It's that vertical piece, right? So that's just something to keep in mind when you're going through these problems, is what you've actually solved for with that value of r, all right? And then if you want to get the horizontal distance that it's traveled, or that tangential distance that it went along the sand, you can get that using trigonometry, since you know that beach angle beta, and you know one of the sides of your right triangle, you can use sine or cosine or tangent or whatever you need to in order to get the other sides of that triangle.